So the last couple of videos, we've been talking about basically these quantum triangles and what they are and everything. And so the purpose of this video, I think, so what I want to do is I want to get to this, I want to get to the point where I can explain this image and how I made them and what they mean,
Okay.
right? And you see in the upper left quadrant, you see how it says inseparable and it says maximum entanglement.
Mm-hmm.
And then in the bottom right quadrant, it says separable. It says separable and minimum entanglement. And then next to it, you see a plot that says curvature singularity. Yeah. So I think that this is an actual image of the geometry of quantum entanglement, like of this is like literal visualization of quantum entanglement.
Mm-hmm.
So in the notes I sent you, it's all about like the focus of the notes was all about separability and the difference between separability and entanglement.
Okay.
So so you have this idea of having a pure state, which is a state that has zero missing information. It has no entropy in it,
Mm-hmm.
and it's associated with the idea of certainty, like being able to know something with certainty,
Yeah.
right?
Yeah.
So remember in the past videos, we keep talking about these triangles, using triangles to represent quantum states.
Mm-hmm.
And we talk about how the points on the vertex are associated with pure states.
Yes.
And then a point in the center is associated with a maximally mixed state.
Mm-hmm.
And so my goal is to explain that image that I showed at the beginning, with the dumbbell looking things.
Yeah. Using the triangles.
Yeah, how do you get from the triangles to the
I see.
dumbbell is what I'm
Okay.
trying to get to.
Yeah.
And and how does quantum entanglement play into this? And how can you
Mhm.
explain this entirely in terms of these triangles?
Okay.
So if we recap, the triangles themselves represent probability distributions. So when we ask ourselves what is a quantum state is just a packet of statistics.
Mm-hmm.
Basically, I have a quantum state, I have these things called observables. I can apply the observables to the quantum state and I get probability distributions. And
Yeah.
these probability distributions are associated with what's likely to happen in a experiment.
Yeah.
So when you look at this green triangle, you have each vertex. I have one of these objects that are like a ket and a brawl that are outer product with each other. Anyway, you
Mm-hmm.
can look at the image. Each one of those are associated with a measurement outcome, and then each point on the triangle is a distribution that shows you if you're likely to see one versus the other. And so this is all associated with the concept of information. Information theory, to gain information is associated with surprise. So that means to gain information, you have to be surprised. So the opposite means that if I have information, then I'm not surprised when I make a measurement because I already had full information, right?
Mm-hmm.
And so in associated with the probability distribution, if I have three possible outcomes and the probabilities are 1, 0, 0, then that means I know for a fact that the probability associated with one is going to happen and the other two have zero probability of occurring. And
Yeah.
so that's how probability distributions themselves can tell you about the amount of information you have. And so with these triangles, I show you the distribution associated with it. So the
Mm-hmm.
point in the center is maximally mixed, where you have a one third probability, which means that it's completely random, and I have no idea what's going to happen.
Mm-hmm.
Then, if you go down to the triangle below that, I have the point at the vertex associated with lambda one, right? So, and then this is what we call a pure state.
Yeah.
So a pure state has complete certainty, probability of one, and zero uncertainty. Yeah. And so do you have a question?
Yeah. Like the triangles, like the triangle here is what's called a simplex, right?
Yes, it's a
Yeah. And
simplex.
then you just arbitrarily chose a triangle, right? Like three vertices, or it could have been any other shape, right?
I chose I didn't choose a triangle. The triangle comes from the fact that I have three possible outcomes of an
Yeah.
experiment and the fact that the sum of the probabilities need to equal one. So
Mm-hmm.
so in other words, probabilities are numbers between 0 and 1, and so if you have three outcomes,
Yeah.
then the sum of all the probabilities has to equal to 1 when you sum them all together. And
Yeah.
that constraint creates the triangle.
Yeah. But you set the stage in a way that there's three outcomes in the first place.
Oh, yeah, I'm just
Yeah.
assuming there's an experiment
That's
with
what I
only.
mean. Yeah. Yeah.
Yeah, yeah,
Okay.
yeah. Yep, that's
Mm-hmm.
at the stage. So I'm saying we said,
Mm-hmm.
let's assume an experiment where there's only three
Three
possible
outcomes. Yeah.
outcomes.
Okay.
Yep.
So this is where the triangle comes from initially. It's like three outcomes, and then we have a simplex called a triangle for now.
Yes. Yes. And and I choose 3 for visualization purposes. Like a
Mm-hmm.
triangle, like 3 outcomes is just really convenient as a space for understanding, visualizing, and teaching.
Yeah. Okay.
Yeah. Yep. And then you can see that in the image below that, I changed the point of the vertex, so now it's on lambda 2. So now this that point is saying that you're guaranteed to see lambda 2, and the other ones have probability of 0. So you have a probability of 1 of noticing lambda 2.
Mhm.
And then you can see something like in the triangle below that, I've chosen the point in between lambda 1 and lambda 2,
Mhm.
where now you have lambda 3 is equal to 0, and the other ones are a 50-50 probability of seeing lambda 1 and lambda 2. So this is what the probability simplex is. All it is a representation of what you're likely to see in an experiment of measurement outcomes, and all quantum states are objects that contain statistics. And for any quantum state, you can always diagonalize it to make it look like one of these triangles. So that's just like a theorem. It's just a fact of
Mhm.
probabilities in the nature of quantum states. Is that if I give you a density operator, which represents a quantum state,
Mhm.
then you can find a representation or a basis for that density operator in which it looks like a simple triangle. So it looks like a classical probability distribution. That's true for
Yeah.
any quantum state.
Mhm. Okay.
Yeah, so that sets the stage for our quantum state. Yeah. So
Yeah.
do you have any questions? That was just the quick recap. So you know that we're starting off from this idea of purity is associated with certainty, full information, no ignorance, um, and that these triangles are merely representing probability distributions of what you'll see in a measurement outcome.
Yeah.
Yeah.
And these lambda 1, lambda 2, lambda 3 are the different quantum states we have.
Yeah, so those would be associated with different outcomes of the experiment.
Okay. And there, when you have the bracket with the lambda 1, that's like in one basis, and we have three bases right now, right?
Yes, yes, yes. So because this is uh three-dimensional object
Mhm.
a three-dimensional experiment with three possible outcomes,
Mhm.
then I have like lambda 1, lambda 2, and lambda 3. Yeah.
Okay. Yeah.
Yep.
Just making that clear for the viewer, so people who, so they have like they start from the basics of what's going on here.
Yeah, yeah. And I think that hopefully that makes sense. Yeah. So now we go to mixed states, subjective versus objective ignorance. So
Yeah.
a pure state has zero ignorance in it, zero entropy, and mixed states have some ignorance or some entropy associated with them,
Hmm.
right?
Yeah.
And so this idea of subjective versus objective ignorance. In the previous videos, we talk about a mixed state, and we talk about it in terms of Alice sending a quantum state to Bob. So in this image, I have Alice at the top, Bob at the bottom, and Alice is sending Bob a quantum state, and Bob is making a measurement of that quantum state. Now, if you're doing an experiment that has like 50 trials, if she sends Bob the same state every single time, then that's a pure state because Bob knows exactly what state he's getting every single time. But what she can do is she can take her 50 trials, and 30% of the time she can send state one, another 30% of the time she can send state two, and then 40% of the time she can send state three. And so that means that when Bob is doing the experiment for each trial, he doesn't know which quantum state he's getting.
Yeah.
And so because of that, there's some ignorance associated with his measurements. There's
Yeah.
uncertainty that's been introduced by Alice's mixing. But I call this subjective ignorance because Alice and Bob, they're both inside of the laboratory. So Alice is in the lab, Bob is in the lab, and she's sending him this information. And because they're all entangled with the laboratory and they're all within this laboratory setting together, Alice could always call Bob and tell him what state she sent. And so his ignorance isn't because there isn't information. His ignorance is just that he doesn't know what it is. But if Alice tells him what it is, then he'll know. And so this is a separation. This ignorance right now is not due to quantum entanglement.
Yeah.
This ignorance is just due to subjective ignorance.
Yeah. Like we can call it like classical ignorance, right?
I suppose you could call it that. Yeah, I suppose.
It's
Yeah,
like ignorance
that's not
due
a.
to not like the information could be accessible. Basically, is what you're saying.
Yes, yes, yes.
That's
I
where
think
the
that's
ignorance
actually
is
a good.
coming from. It's not
Yeah, I think
intrinsic
that.
to how things are.
Yes, yes, yes.
Mhm.
I think that's a good way of putting it. Classical ignorance, and I think it's good because this idea of being in a laboratory, like the
Mhm.
room you're sitting in right now, you're entangled to all of the stuff in the room. And actually, I think that this is where time comes from. You know, why there's time is because if you're sitting in your room, everything is bouncing off of each other. You know, you have
Yeah.
light from the sun that's coming off and bouncing off of you. You're in a room, and all the air is bouncing off of you. It's bouncing off the walls. Your walls is attached to the house. The house is on the earth. Like everything's connected to each other.
Mhm.
And so, because everything's connected to each other, if the sun moves, then that changes your state in your room. So you have no control over that. So
Mhm.
when things happen out in the world, because everything's connected to each other, then that means that your state has to evolve with it
Yeah.
because you're entangled to the entire world. And that's where time comes from.
Mhm.
If it was the case that you could be completely isolated from the world, such that when things happen out in the world, it doesn't change anything about your state, then there's no time. And that's exactly what a unitary transformation is. And so that's what we're talking about in today's video, is that purity, separability is associated with no entanglement and thus no time. And that's what we're talking about here.
Yeah, and that correlates with zero entropy.
Yes, associated
Mhm.
with zero entropy.
Mhm.
Yeah. Yep,
Yeah.
yep, yep, yep. Yep, yep, yep. So yeah, that actually segues quite nice. Yeah. So yeah, so now we want to go into entanglement and objective ignorance. All right. So in this image, what I'm trying to communicate is exactly what I just said. Alice, like all of the red stuff that I put in there looks like random noise. That's all the chaos of everything bouncing off of each other and connected to each other. That's what
Yeah.
that's supposed to represent. And
And we
then the blue,
that's the environment basically in
yeah,
physics.
that's the
That's
environment. Yeah.
yeah. Okay.
And then the blue circle is supposed to represent a isolated, pure quantum state.
Mhm.
So that thing is isolated. It's pure. It's, it's sitting in the corner by itself. It's not interacting with anything. That's why you don't see any red lines going through it.
Yeah.
Whereas with Alice and Bob, you see the red lines going through it. So in this picture right here, I'm trying to communicate something about the state being separable. And before I was going to communicate this later, but think of it as something like a refrigerator. So think of the blue circle as being a cold spot in a room. When you have a refrigerator, like what does the refrigerator do? It takes a volume of space, a volume of a room. It insulates it. It insulates that volume from the rest of the room, so it's creating separability. So it reduces the amount of interaction between the environment and the volume inside the refrigerator. And then it pumps energy outside of that volume to cool it down.
Yeah.
So it creates a cold spot in the room.
Mhm.
Think of that as that's what a quantum state is.
Yeah.
So think of a quantum state as a cold spot in a room, and so now imagine that you open up a refrigerator so that it's no longer isolated. What happens, right? What happens is that cold spot in the room then interacts with everything else in the environment, and then it diffuses and warms back up.
Mhm.
So you took something that was in a low entropy state from the isolated portion in a room, and you took the entire room as a whole, and you've taken a small portion of it, and you've cooled it down and made it more ordered. So you've reduced the entropy. But then when you open the refrigerator and let everything else interact, then you increase entropy.
Mhm.
And so what I'm saying is that when you have the state in the environment separated, then you have your pure quantum state. But once you allow the state to interact with the environment, then you have an increase in entropy. And this is associated with the surfaces of ignorance. Those geometries, those pictures I showed you at the beginning, those are the surfaces of ignorance, and those are the things that are associated with the increase in entropy or the volume of.
Yeah, but yeah, I don't know. I feel like you made a big jump now. Like
Okay.
you were explaining like an analogy between the refrigerator and the quantum state.
Hmm.
And okay, like when we interact with the environment, the entropy increases, and that's what's called entanglement.
Yes.
More, what do they call it? Freedom. What's the
Mm.
word? Something of freedom.
Degrees of freedom.
Degrees of freedom. Yeah, like more degrees of freedom now, more entropy. But then you jumped right to the surface of ignorance, and like
Yeah, yeah. I shouldn't have done that. Yeah.
I feel like there's a disconnect here between this idea and then jumping over to
Yes,
that.
yes, yes, yes. So
Mhm.
so yeah, so let's go ahead and pin that because you're absolutely right. I did jump, and I think that if
Mhm.
we just continue with
Yeah,
what was
then that
planned,
would
then
make more sense.
we'll get there at the end.
Mhm.
Yeah. And so far, all I want for everyone to understand is that this picture represents zero entanglement. So
Mhm.
when you go to the next slide, I have the equation written down to represent this system,
Okay.
where it says state of the joint system.
Yeah, yeah.
So yeah, so for people who are unfamiliar, like this notation that I'm using with this vertical bar and then this what we call a ket, well, yeah. Anyway, this notation is called is a notation created by Dirac. It's called Dirac notation, and it's used to represent quantum states. And so in this system right here, I have phi s, which represents the system, and then I have phi e, which represents the environment, the lab. And this circle with a cross through it represents something called a tensor product. And by definition, within the mathematics of quantum mechanics, if you can write down your quantum state as a product state in this way, then we say that the two states are separable. There's no entanglement. This is like a definition of entanglement. If you can write your state this way, then it's not entangled. They are separable. They are isolated from each other, and that's what that means mathematically. That makes sense?
Yeah.
Yeah.
And then
Okay.
we make the joint state. That's like the tensor product between the two, and that's a
Yes.
new state entirely.
Yes. So basically, a quantum state 1 phi s lives in Hilbert space S. Quantum state 2 phi e lives in Hilbert space he, and then a
Mhm.
tensor product I call HFE, which is a higher dimensional space in which the joint system lives in this higher dimensional space.
Yes. Okay. Makes sense.
And yeah, and this entire idea then means that when you have an object that lives in the joint space, the higher space, I can always do a process called a partial trace, which takes the
Mhm.
object in the higher space, and I can look at only one subsystem. So I can go, okay, I have the joint system in the higher space, and now I just want to look at the information associated with one part of that state. You do a partial trace, and now you can look at a subsystem.
Yeah.
Yeah.
Okay.
So that's really important because it's gonna indicate like this is like doing that process is a process of measuring entanglement.
Yeah. And so far, this is just all mathematical. Like we have these two states, which are like vectors, basically, right? These two
Yes, they
quantum
are
states.
vectors. Yep.
Yeah. And then we're doing tensor product between them, and then we get a new space. And then you're saying we can do a trace, which is another mathematical tool we have, and we can trace back to the individual
Yes.
states, right?
Perfect.
Okay.
Yep.
So far, it's
Exactly.
just math. Okay,
Yep.
I get it.
Yep. Yeah. And so yes, we went from a physical picture to
Mhm.
what the mathematics looks like to represent that physical picture. Yeah. All right. So now we're going off to the handwritten notes.
Yeah, I have 'em.
Okay, now my thought process was to like the thought process is something like, okay, we have these triangles, right? And we know that vertex on the triangle is associated with a pure state. And we know that if you have two states, system and environment, and they have no entanglement with each other whatsoever, then the system, the little blue circle, that is going to be a pure state. So purity is associated with separability, is associated with no entanglement. That's the important thing. Purity is associated with separability, which is associated with no entanglement, which is associated with a vertex on that triangle. So that means that in this case of the objective ignorance, when I go from a vertex on the triangle and I start moving to the center of the triangle, then I'm losing separability, I'm losing purity, and an entanglement is being created. So points on the center of the triangle are associated with entanglement. Yeah. And so what I want to do, because this series of videos I'm doing with Hussein, the purpose is to actually do research. Like if you're watching this, then our goal is for you to be able to understand what's going on so you can actually participate in the research. And so given that equation of phi SE equal to phi S tensor product phi E, now I want to do an actual example and go through the math of what it looks like when you have a separable state versus an entangled state. And
Mhm.
what that looks like when I go from the composite system down to a subsystem, what that looks like. And what you'll find is I can explain that in terms of a point on the triangle. So yes, that's good so far?
Yeah, that's really
Okay.
good.
Okay. So we start off with system in our environment. So I'm writing down the equations explicitly now. So we have phi s is equal to this 1 over square root 2, 0 plus 1. And if you don't understand what this is, just relax. If you're watching this, you don't need to understand exactly what these things mean. It will unveil itself as it goes. I used to tell my students this when I was in grad school. Like whenever we'd be connecting circuits, I had this foolproof way to understand how to connect a circuit. And I'd tell them like, don't think, just follow mindlessly. And so that's what I
Yeah.
need you to do right now.
Mhm.
Yeah. So writing this down, I can show you exactly how this tensor product works, like how you go from phi s to phi e, and then you make it into phi se. And it really is just basic multiplication. Like if you look at these little kets, then you have one here, and it's just you're just doing a commutation to like multiply them out. And so you can just see that, right?
Yeah.
You good, Hussein? Yeah.
Yeah. Yeah.
Yep. So that's just page one. That's the first part, just multiplying these things out. And so the thing at the bottom of the page, that is the joint system. But
Yeah.
remember, I started off with two separable states. Yeah, I started off with two separable states. So the joint system just looks like that. Now the thing is that these things that I've done, like for my research, you need to be able to do computations with them. So if you're looking at these sideways triangle thingies, you're like, what? How do you do a calculation? Like, what is that? A number? Like, what is that? And so in quantum mechanics, you can represent these things with arrays or vectors. And so in the next page, I just write down how we write these things out in quantum mechanics. Like this is just, again, don't think about it. You can pick up your quantum mechanics textbook. You can just go to the page and it says, this is how we represent these things. This is how we turn these things into vectors. And
Mhm.
so the 0 represents the vector 1, 0, and the 1 represents the vector 0, 1, right? And so now that we have these vectors of the
Yeah.
0 and the
Actually,
1,
it's like important to note that like the like the zero with the dash and the triangle on the right, like, that doesn't represent zero. That represents a vector.
yes, it represents a vector,
Yeah. Yeah.
exactly. Yep, yep,
Okay.
yep, exactly.
So like the 0 and 1 on the left don't really matter. Like we were just it's just a notation to show how like to distinguish between one and the other, right?
Yes, 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 yes. It's the idea of like a bit. So like if you
Mhm.
had a quantum state, then that was like classical, the 0 represents like 0 or 1. Like it can be plus or minus, it can be up or
Exactly.
down, it can be
It's not
anything, it
like
doesn't matter.
it's not
Yep,
like
yep, yep.
0 is nothing and 1 is 1, like number 1. We're just representing them in different ways. But what's important is the vector 1, 0 and 0, 1. Those are like real
Yes, those are the
numbers
real
that
objects.
we're gonna use them to operate.
Yep, yep, yep. To do
Mhm.
actually do a calculation.
Yeah.
Yeah. And so now that you have this representation of this 0 vector as 1, 0 and 1 as 0, 1,
Mhm.
we can then show you how to do the tensor product. And again,
Yeah.
this tensor product is just a mindless mathematical like thing. Like this is how it works. And so I
Yeah.
wrote it out explicitly that to write a tensor product, you take basically if I'm doing 0 and 0, then I take the first part of the 0, which is 1, and then I multiply that by the 0 vector, and then I take the 0 part and I multiply that by the 0 vector. And so if you look at this, you end up getting the vector 1, 0, 0, 0. And so I
Mhm.
went from having vectors that exist in the two-dimensional space of 1 and 0 to a vector that lives in a four-dimensional space. So that's going
Yeah.
from H and HE to HSE.
Mhm.
So so when I do that for all of the vectors possible, which are in the quantum state that I showed, the 0, 0, 0, 1, 1, 0, and 1, 1, then I get these vectors 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. It's just
Mhm. Yeah,
basic
it's
math.
great.
So now what that lets us do um is let us write out the quantum state in terms of these vectors. And so page 3 is just me stating explicitly what I just said about I have the basis of HS and I have the basis of HE. And then when I do the tensor product between those bases, I get the bases of HSE. So I just
Yeah.
wrote that out on page 3. Yep.
Mm.
So and then on page 4, now these vectors, like remember these ket things, these are vectors. And so to turn them into a matrix, you can turn them into density operators. You have to do something called an outer product. And so if you look, the phi SE, I have capital phi SE, and then I take the tensor product of just the vector phi SE, and then that gives me what the matrix looks like, which is just 1/4 equals all this junk. Does that make sense? I should probably mention that one thing about the bra and the ket is that the ket looks like this, and the bra looks like this. And so to go from the ket to the bra, you do a transpose. And if it's a complex number, then it's a complex conjugate transpose. But right now we're only dealing with real numbers, so all you need to know is that you just do a transpose. So the first vector was a column vector of 1, 0, and then and so that represents the ket. But then when I represent the bra, then it becomes a row vector of 1, 0. And so that's how you do the tensor product. You have your column vector, and then you turn it into a row vector, and then you just multiply those together in the way that's consistent with linear algebra. So it's just basic linear algebra, like high school linear algebra.
Mhm.
And then that gives you a matrix.
Yeah.
And so that's what I'm doing on page 4. I'm just going out through explicitly, and I'm writing out the state in terms of its ket and bras. And then below that, where I say recall, I'm just showing you how I take each one of those elements and turn it into a matrix.
But what's the goal of all this? Like, what's the reason of doing this?
The goal is to, because we started off with the picture of having the environment and the quantum state, and we're
Okay.
saying that these things are separable. And then I
Yeah.
wrote down the equation phi SE is equal to the tensor product of phi S, a tensor product phi E. So I'm going from a conceptual picture to the actual math. So this it's like looking under the hood of a
Yeah.
car.
No,
It's like
but
this is
I
the
get that.
machinery.
But now we did the tensor product between the two substates, we can call them.
Mhm.
And then we have a higher dimensional state made up
Yeah.
of the two.
And so right now, what we're looking at is what that higher dimensional state looks like.
Okay. And then we were converting that into a density operator on page
Yes.
4.
Yes, yes,
Okay.
yes.
But yeah, well, why are we converting to a density operator?
Ah, so I guess just in my mind and just how I think about it, this just most convenient way of showing how I go from a composite system to a subsystem.
Hmm. Okay.
It's just the mathematics of partial trace.
Okay. Okay.
Yeah. Yeah. Um, yeah, so at the bottom of page 4, this is what the quantum state looks like as a matrix, the joint system.
All right.
Yeah. Hey everyone, Dr. Ray here. I'm just interjecting in the video real quick. In my original recording with Hussein, I didn't explain the partial trace well, so I want to just explain it really quick. Because remember, the point of these videos is that this is a research channel, so I actually want to explain the mathematics of what's going on so that you can follow along if you like. And so, what we've done so far in the video is that we've constructed a composite system from two subsystems that are uncorrelated with each other. So, if you have a composite system that's made up of multiple objects, you can always cut that system in half and then only look at one part of that system. And so to do this, you do a mathematical process called the partial trace. And so in this little section right here, I want to explain how to do a partial trace because this is important for computing things like entanglement. You can compute something like the entanglement entropy, where if you take a composite system, you do a partial trace, you look at one subsystem of the composite system, and if you find that it is not pure, so you find out that it's mixed in some way, then this can be an indication that the two composite systems are entangled. And if you do a partial trace and you find that one of the subsystems is pure, then you know that these things are not entangled. And so that's the purpose of this. I'm currently doing an example where I took a system, two subsystems that I know are not entangled, produce a composite system, and then I want to do a partial trace to show that when you look at a subsystem on its own, you get a pure state back, thus demonstrating that they are separable and not entangled. And the purpose to this is that after I do this example, I'm going to do an example in which you have an entangled state, and then I'm going to take a composite system that's entangled, and then I'll look at a partial trace, and you'll see that this thing is not pure. And in fact, it's maximally mixed because I'm going to use a Bell state, which is a maximally entangled state. And so what I'm going to demonstrate is that when you take a composite system and you compute the partial trace, if the thing that you get at the end is not pure, then that is an indication that the two subsystems that make up the composite system are actually entangled. That's the purpose of this example. Imagine that you have two subsystems. One lives in Hilbert space HS and one lives in Hilbert space HE for system and environment. And so imagine that HS, the dimension of the Hilbert space of the system, has a dimension ds, and imagine that the Hilbert space of the environment, HE, has a dimension DE. And so in the example I want to use, dimension of Hilbert space S is 3-dimensional, and the dimension of Hilbert space 2 is 2-dimensional. Now, when you make a composite system, you're essentially multiplying them together. So the dimension of the composite system, the Hilbert space of the system and the environment, will be 3 times 2, so it'll be a 6-dimensional space. And when you have a 6-dimensional space, then that means that your density operator that represents the composite system is going to be a 6 by 6 matrix. So once we have this composite object, we now want to break it down into its subsystem using the partial trace. So in my little handwritten notes, I have the partial trace defined. So you can take the partial trace where I look at the system, or I can take the partial trace when I look at the environment. And we call it the partial trace because you're taking the composite system and then you're tracing out the environment. And that leaves you only with the system. Or I'm taking the composite system and I'm tracing out the system, leaving only the environment. And so what I have at the bottom is just a general definition of what that looks like. And that looks like a whole bunch of gobbledygook. I don't expect you to understand this or care about this. And that is just the technical definition that is given. But what I want to do in this example is I want to show you how this is done on a matrix. So again, don't bother yourself with saying, I don't understand what these symbols mean. That's not a problem. just mindlessly follow the procedure I'm going to give you. If you have a density matrix that represents a composite system and you know the dimensions of the subsystems that make up the composite system, then you just mindlessly follow this procedure given a matrix. That's it. That's all you need to worry about. And so in this procedure, you take the composite, the density you take the matrix that represents the composite system and you break it up into a bunch of sub matrices. And the way you break it up depends on the dimension of the system. And so in this case, because the dimension of the system is 3 and the dimension of the environment is 2, then I break up this 6x6 matrix into 9 2x2 matrices. And so, and if it was the other way around and you had a 2-dimensional system and a 3-dimensional environment, then you would break that thing into 4 3x3 matrices. So that's just the mindless procedure that you do. To find the matrix that represents the subsystem S, you take the subdivided matrices, and you just add their diagonal elements. And then each one of those adding the diagonal elements makes up the elements of that matrix. That's it. It's that mindless. You just go, okay, I have a matrix. I know the dimension. I chop it up into sub matrices based off of my knowledge of the dimension of the system and the environment. And then I just take each one of these sub matrices and I just add their diagonals across. And each one of those adding of the diagonals makes up the element of your matrix that represents your system, your subsystem. And so for the environment, it's a little bit different. Instead, what you do is you just take all of the diagonal matrices, these sub matrices that you make, you take the diagonal sub matrix and you just add those together. So you'll end up with a 2x2 matrix. And that would be the matrix that represents the subsystem of your environment. And that's it. It's just a mindless procedure. And so applying this to the example that we have, because we started off with a system and an environment that are both 2-dimensional, then my composite system, the matrix of my composite system is going to be a 4x4 matrix. So I break that into 4 2x2 matrices, and then I just use this mindless procedure. And in this case, because I started off with 2 subsystems that were identical, then what I get is this result at the end. And so this result right here, this is the original matrix that I had, because remember, I took 2 things that were not correlated to each other. I made a composite system, and then I separated them back out. And because they're not correlated with each other, then I should just get back the original matrix that I had in the beginning, which is what I get. And again, the reason why I'm doing this is because I want to show you the mathematics of how all this stuff works. So this is just a good example to just turn the crank and understand the mathematics. And then I'm going to contrast it with an actual entangled system so that you see that when you do this the exact same procedure, but you start with an entangled system, you don't get back the 2 separable subsystems matrices. That's not what you get. And then you use these subsystem matrices. Once you get these, you can use them to compute purity, or you can use it to compute like the von Neumann entropy of these things, and that will give you your measure of entanglement. And so that's the reason why we're doing this. Hopefully this helps, and hopefully this is useful.
Now, what you're doing is just pure math, right?
Yeah.
Where are you trying to get at? Like, you're doing the trace so that what's the conclusion that you're trying to get to?
So basically, this is the mathematical process for taking a joint object and then
Mm-hmm.
going down to a subsystem, so that you
Yeah.
end up with an object that only has. So you end up with an object that's only associated with the subsystem, and then once you have that object associated with the subsystem, I can compute its purity, and then that purity tells me whether it's separable or not. If I go down to the subsystem, if I take the joint system, go down to a subsystem, and then I compute the purity of the subsystem, if that thing is pure, then it's a point on the vertex of the triangle, and there's no entanglement between system and environment because purity is associated with separability.
Yeah.
If it were the case that I were to take my subsystem, if I take my composite system, go down to a subsystem, and it's not pure, then that means there's entanglement. Assuming that you're starting off with like a pure. 'Cause I mean, I could take a state that's mixed or somehow, and then put it into an environment, and you separate it down, and it might not be pure, but that's not due to entanglement. That's just due to the fact that the thing wasn't pure to begin with.
Yeah, to
But
begin with. Those are-
yeah, but if you're assuming that you're starting off with something like a pure state, and then I do the separation process, if the thing in other words, if you do a partial trace and you get something that's pure, then guaranteed 100% these things are separable and not entangled.
Yeah. But then didn't we make that assumption in the first place? That they are separable?
Yes, yes, yes. So this is the point. The first example is example of a separable thing where we go through the mechanics of the math. The next example is an entangled one. So then you see how an entangled system behaves differently.
But this is, right now, what we're doing is all separable.
It's all separable.
Okay.
So we started off going, look, I'm gonna start off with two quantum states, and they are pure on their own. They're completely have nothing to do with each other. They're
Okay.
separable. I'm gonna take those things, make a composite state, so that I know for a fact I start off with something separable, and then I'm
Hmm.
gonna do the partial trace process and show you that I recover a pure object. So this is
Yeah.
what it looks like when things are pure and inseparable and there's no entanglement. Then I'm
Oh,
gonna
so you're just trying to show that. You're trying to show that. It's not
yes.
something you're trying to get at. Trying to, it's not like trying to discover something. You're just showing us that you can go back and forth basically because they're pure state.
Yes, I'm trying to
Okay.
take the visual picture of the laboratory in the
Mhm.
blue circle separated, and then I wrote down the mathematical equation. I'm going like this is how we encode this concept of using math. This is what it looks like.
Okay. Okay. Now I
Yeah,
understand what's going on here.
yeah,
And
and
the
so
rest is
and so
just basic math. It's not like
this nothing
anyone can
special.
yeah, anyone can look it up and then understand what's going on with traces and all this like mathematical tools.
Yes, yes, yes.
Hmm.
Yeah. And so yeah, I mean, I guess it's a matter of I guess my desire for
Hmm.
people to have something tangible to hold, so it's not
Yeah.
just concept space. It's like, no, this is hard. This is the actual math. This is the
Yeah.
math that I use to do my research. And if you follow this channel and watch this video, don't forget to like and subscribe. If you follow this channel and watch this video, then you can actually do research with me because this is the
Yeah.
math that you have to know to do it.
Okay.
Yeah. Yeah. Really, yeah, yeah.
And trace is like conceptually what is trace so like the viewers know.
So right now there's a difference between trace and partial trace. Right
Okay.
now we're taking a partial trace,
Partial trace. Okay.
which is to take a composite system and then look at only one of the subsystems. It's like the example I use of ripping a piece of paper that I'm going to
Yeah.
use later on, where it's like I have a message that's written on a piece of paper, and then I rip the piece of paper in half, and that's what the partial trace is. It's like saying I have the one piece of paper which exists in the composite space. I rip it in half and only look at one part of the paper, and that's looking at a subsystem.
Hmm.
So you're just throwing out the rest of the information. That's what it is. Like the partial trace I've written is tracing out the environment. So I'm taking the environment information, I'm just tossing it away, and I'm looking at the information left with the system.
Yeah. But then in this case, the information you're getting left, it's still full information.
It's still full information because they're not
Mm.
entangled. Yes.
Okay.
Yes,
I
yes,
see.
yes. Yep.
I got it.
Yep. Yeah. So, okay. Yeah. I mean, we're definitely going to edit out some stuff there because I think, but at the end of page 5, do I write it down? Yeah. At the end of page 5, I have equation 1, and that
Yeah.
is the system that is phi s. That is the information associated with the system. So that's the equation 1. So after you do the partial trace, I get an object that lives back in the two-dimensional space.
Yeah.
I
Yeah,
took
that's
an
what the
object.
trace is. Oh,
Yeah, that's what the partial trace is. So at the end, I have this
yeah.
thing. And
And
so now,
we can go way back to actually no, if we go way back to page 1,
yeah.
that's oh no, this has nothing to do with page 1, right?
Well, page 1. Well, so basically, if I mean, if it does, so if you go back to page 1 and you see phi s,
Yeah.
if I were to take the outer product of phi s to make it a matrix, that's what equation 1 would be.
Okay.
So you can go directly to equation 1 at the bottom of page 5. You can go directly to that from the definition of phi s on page 1.
Yeah, yeah, that's what I thought.
Yeah, you take the outer
Mhm.
product and you get that back again. Yeah.
Okay. But you did it a different way. You did the tensor product and then partial trace back.
Yeah, yeah, yeah. Just to show that that the
Okay.
state is they're not entangled or anything.
Mhm. Alright.
So now, and I've already went over this on page 7. I just talk about the idea of purity. So this goes
Yeah.
back to what. So I wrote these notes before I introduced the first part, where I say, okay, remember these quantum states themselves are points on a triangle,
Mhm.
and when I do the partial trace, if they're separable, then I should get something that's pure, which is a vertex. And so then the way we compute the purity is we take the density operator and we square it. So we just take the density operator and multiply it by itself, and that's taking the square of the matrix, just multiply matrix by
Okay.
itself, and then we take something called the trace. Now the trace is different from the partial trace. The trace is all you're doing to take the trace is you sum up the diagonal portions of the matrix. So I take my density operator phi s, I multiply it by itself, and I just add up all the numbers on the diagonal, and that gives me my purity.
Mhm.
And so the purity can have a value between 1 over d, which is the dimension. So in this case, it'd be 1/3, which is a maximally mixed state, no purity, and 1. If you compute the purity and you get the number 1, then it's a perfectly pure system. If you get
Mhm.
anything less than 1, then it's not pure. It's mixed.
Okay.
Yeah.
That was a lot.
Yeah, and the reason why the trace is associated with purity 1 is because the trace is the same, like, because it's literally just I take a matrix and I just add together all the values along the diagonal. That's how you compute the trace. It's really simple.
Mhm.
But for a quantum state, for something to be a valid quantum state, that has to equal to 1 because it represents probabilities. Because remember, the density operator, I can always diagonalize it.
Yeah.
And so if I diagonalize the density operator, it has zeros everywhere, and then it just has the probabilities along the diagonal.
Mhm.
And the thing about a pure state is that when you write down a pure state, it's gonna be just the value 1 and 0 everywhere else because it's just a single vector.
Mhm.
So a pure state is always going to just have the value 1 somewhere and then zeros everywhere else. And so when you multiply that vector by that thing by itself, you get the vector you get the matrix back again. So you just have 1 here, 0 everywhere else. You add, you just get 1 back always.
Okay.
Because pure
Mhm.
states are just one-dimensional vectors.
Okay.
Like, I mean
Oh,
I mean, that's the reason why it's a vertex on the triangle. It's just that one
mhm.
vector. That's all it is. So it's a one-dimensional object, and if it's pure, it'll always give you a purity of 1.
Mhm. All right.
And so this is a measure of entanglement, because in this entire example, what I'm showing at the end of page 7 is that if I compute the purity of the object we get after our partial trace, I get the value 1 back again, which means that this thing was always pure, it was always separable, there was no entanglement ever.
Okay.
Yeah.
Yeah,
So
that's what we're
that's what
showing here. All right.
that's what you get at the end of page 7. Yeah, so and then this is just so on page 8 is just me stating exactly what I just said, where I just said exactly what I said. The purity has a value of between 1 and D and 1, and yeah, I just basically said exactly what's on page 8. There's no reason
Mhm.
to go over it again. Yeah. So then page 9. So now page 9 is where we get into the interesting stuff. So now let's write down a maximally entangled state. So this is what we
Mhm.
call a Bell state in quantum mechanics.
Okay.
And so when you look at equation 1 on page 9, I have phi SE, which is a single ket that exists in the composite higher dimensional, and that's equal to the 1 over square root of 2 times 0, 0 plus 1, 1. And the thing is that 0, 0 plus 1, 1, that can't be written as a tensor product between two subsystems. So in the previous example, I started off by saying I have two subsystems. I'm just going to tensor product them together, and then I'm going to do all this crap, and then I get back clearly something that's separable because by definition they can be written as a tensor product. Equation 1 can't be. So when I write down the matrix representation of phi SE, I'm going to write that down. I get this 1/2 with like in the corner and 0 everywhere else.
Yeah.
You see that?
Yeah.
So that's the equation for the density operator of the composite system. And so we're just gonna do our partial trace procedure on that. And that's what it looks like. And now I'm gonna do the partial trace, and we're just gonna see if it's pure or not.
Okay.
And that's it.
All right. Yeah.
Right? Yeah. So going to page 10, I apply the partial trace procedure that I explained in the previous example. And when I take the partial trace where I trace out the environment, what I get is the matrix 1/2 1 0 0 1. So I get 1/2 times the identity
Okay.
matrix. And so if I take that matrix, multiply it by itself, and add up its values along the diagonal, I get a value of 1/2.
Yeah. Which is not 1. It's less than 1.
Remember, the purity can have values between 1 over the dimension and
Yeah.
1. So
Yeah.
it's literally the smallest value of purity you can have. And so what that means is that it's maximally mixed. So this density operator, so the information, so I take this composite system, I look at one subsystem of it, and the information contained in it is 0 information. It literally has
Mhm.
no information in it at all. And so what that's telling you is that is maximally mixed. So now that we have gone through the mathematics, like, we can explain it conceptually. Like, what does all of this mean?
Yeah.
Like, what did we do when we did the partial trace? So the first example, like the separable example, the first one that we did, that's equivalent to this piece of paper where I have a piece of paper that's folded in half. On one half of the paper, I have the phrase "I have your dog," and on the other half of the paper, I have "John has gray hair." Now, these two messages have absolutely nothing to do with each other.
Yeah.
They're completely separable. They have nothing to do with each other whatsoever. And so if I were to rip the page in half and get rid of the left portion, all I have is John has gray hair. And if someone received that, they'd be like, okay, I got a fully clear message with no missing information. I now know John has gray hair. There's no confusion here.
Yeah.
Right? So that's a pure state. And I can do the same for the other half. If I get rid of the right side, I have the phrase, I have your dog. And so it's like, again, I have a completely full information, nothing's missing, makes perfect sense. I
Yeah.
now know that this person has my dog.
Okay.
But then if you go to the next example, I have written on this piece of paper, I wrote across it, everyone I know eat hot pockets for breakfast. But if I rip the page in half now, then I have young one eat pockets act fast. It's
Mm-hmm.
like, okay, I could probably guess what that means, but I've clearly lost some information, like what's
Yeah.
going on. And then on the other side, if I get rid of the other half, I have everyone I know hot puff for brr. So
Yeah.
now it's become less coherent, you know?
Yes.
And so that's because these messages are correlated to each other. They're not separable.
Yeah.
They're entangled.
Yeah.
And so the more entangled they are, when I throw out the information of the other one, the less coherent what I have left is. There's
Okay.
nothing, and so a maximally entangled state is one where if I throw out the information from the other one, then the thing I have left is total gibberish. That's how you know they're entangled. They're not separable.
Yeah. All
Yeah,
right.
yeah. Does that make
Makes
sense?
complete sense. Yeah. Yeah.
Yeah. So I say at the end, the partial trace procedure is the splitting the paper in half process.
Yes.
That's what it is. Yeah. All right. That makes sense.
Yeah. That makes a lot of sense. Like easy to follow.
Yeah. 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 So explain the math. What does separability mean physically? Remember the goal is to get to an understanding of these geometries I said at the beginning, how they're associated with entanglement and the triangles. Yeah. So one of the things that I kind of wanted to communicate is like what are quantum states ontologically, like what is actually physically there.
Yeah.
And so we've done this entire example where we started off with a separable state, a system and an environment, and we use the idea of a refrigerator and cooling something down
Uh-huh.
to explain like how the quantum state was made. And when you did that, you separated the quantum state from the environment. And so that process of separating is a process of erasing correlations. Like you've removed the correlations between the system and environment, and you've created this quantum state. And so that means that if I were to start off with an environment where everything is entangled. Like I don't have any quantum states. All I have is like a bunch of energy and matter that's all like moving around and connected to each other. Right.
Okay.
Uh, so in this case, think of this as the state. This is like the state of the environment before you've created your quantum state. So it's like the system and the environment is just all entangled with each other.
Okay.
And so the red stuff is supposed to represent like energy and matter, right? And all the different shapes stuff is supposed to represent the configuration. So in physics, when we're defining the state of a system, we define it in terms of its degrees of freedom, which are its properties, and the settings of its degrees of freedom. And so what that gives us is something like a configuration. And so what I'm saying is that for this environment picture here, the energy and matter is in some configuration, which tells you the state of the environment, like what configuration it's in. It's a difference between like a room where all the particles are in a corner of the room versus a room where they're all scattered all over the place, right?
Yeah.
What their position and momentums are tells us the configuration of that system. But the problem is that if you're trying to define the state of a system, then that information has to be stored in energy and matter. And so it's the idea of trying to give infinite precision. Like, what if you ask yourself the question, what is the exact state of the environment? If you ask that, then you would need something like infinite precision values of the degrees of freedom. You'd have to know what the momentum is of each particle to infinite precision, for example.
Okay.
And so that would require infinite energy to store infinite information.
Yeah.
So what I propose is that within this closed system of this environment, you have information limits. And beyond that information limit, you have voids. So when I'm talking about what I think of physical, what is ontologically present when describing what a quantum state is, I'm describing it as a void, a symmetry that exists beyond the limits of precision. And so within this environment, even though you have some sort of configuration that's associated with this scribbling of these red lines that I've drawn here, even though you have that, you have to imagine that there are these voids everywhere in this space. So the closed system has energy and matter, which defines its configuration. But with each configuration of energy and matter for any portion of the system, there's a void associated with it. So in other words, I'm trying to say is that there is a finite amount of void because this system itself has a finite resolution. Does that make sense?
Okay. Yeah.
So I'm saying, like, take this lab picture I have with E. Within, it's a closed system, so there's no information or energy going in and out of it. It's a closed system. This closed system has a configuration, but this configuration has finite resolution because it doesn't have infinite energy and energy and matter to say what the state of the system is exactly.
All
And
right.
so within the finite resolution, there's a finite amount of void as well, which is to say a finite amount of incompleteness associated with the degree to which the system's not defined. And so what I'm saying what a quantum state is that when you're creating the quantum state in the lab and you're doing this process where you're creating a separable pure quantum state, what you're doing is you're doing something like you're taking void, you're making like concentrated void. You're taking this lack of resolution that exists everywhere within the system that hasn't been coalesced at all, and then you're doing a process that removes correlations, that creates isolation, and this isolation process is concentrating void in one spot. And that concentrated void is your quantum state. Does that make sense?
I'm not sure. So
So the idea is that the configuration of energy and matter is like constraint data. So in this example, I start off at the bottom and I'm saying something like, imagine trying to find a point in a continuum and I give you the information 0.65.
yeah.
Okay, so if I give you 0.65 to try to define a point, for every value after the 5, there's nothing defined. And so if you go to the interval above, like in the second interval, the one above the 0.65, all of those values past the 5 are symmetric with respect to 0.65. So it's like a border. So the first 0.65 excludes anything that doesn't have the first values of 0.65. But then all the values after the 5, because they have 0.65, they're all symmetric. So think of that as being like your void. It's like your symmetry. It's your freedom.
I don't understand how you're connecting that to symmetry.
So I'm saying something like, I'm trying to find a point in a continuum.
Yeah.
I give you the constraint data 0.65, so it creates a border.
Yeah.
Everything that is not consistent with 0.65 exists outside of it, and everything
Okay.
that's consistent exists inside of it.
Okay.
So when you look at that picture, the second interval is supposed to represent everything inside of the point 0.65.
Yeah. Yeah.
So what I'm saying is something like all of that exists in this hole. So this
Yeah.
hole is the void because 0.65 is your precision, it's your resolution.
Mm-hmm.
Everything in here is the whole. So in other words, if it was the case that I could only look up to the resolution of 0.65, like that's the extent to which I could gather information, and I couldn't see anything beyond that, then that's like a pixel. Everything in here is just going to look the same. I can't distinguish them.
Okay.
It's basically like the concept of a pixel.
Okay, but then you can zoom in even more if you
Then you
have the
can
ability to.
Yes, and then if I give more constraint data, then I zoom in even more. So that's what
Okay.
the next line is. So it's like, okay, now let's
Yeah.
add more constraint data, 0.652. So now
Yeah.
say I add an extra digit of precision. Well, that shrinks the hole. It shrinks the hole, and now there's less things that are symmetric. And so the
Yes.
more data I give, the more constraint data I give, the more information I have, the smaller the hole becomes.
Okay. And you're trying to like go to the extreme, like make the hole as small as possible, is what you're saying, and then you get a void.
What I'm yeah, something like that. Yeah, exactly. So that's exactly what I'm saying. So in other words, if I have an environment, if I have a state of a
Mhm.
system like this environment, and I ask the question, what is the state exactly? So
Yeah.
exactly is the idea of zooming in. It's like,
I
okay, I'm
see.
trying
I
to
see.
get
Yeah, yeah, yeah,
infinite
yeah. Okay,
precision.
so you have a system, and you're trying to zoom in like this, like the number line. You're trying to zoom in on 0.65, but you're doing it with an actual object, right?
Yes, 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 yes.
And the only thing we can know about these subatomic particles are like, the position and momentum and all that. So
Something
this is
like
what we're
that. Yeah,
trying to know about them. So this is all we can know anyway about any of these like very small particles. So then
yeah.
you're trying to zoom in on it, and then what follows from that?
I think you hit the quantum. So
Yeah.
I'm saying something like from a classical picture, from a macro picture, you're looking back at it, you're saying, oh, well, classically, this state has each particle, I can give you the momentum and position. Say I have 5 particles, and this one has momentum of point five six
Mm.
three four two eight nine. It's like, well, okay, you can give the precision of momentum up to a point, and you can say what the
Yeah.
state of the system is up to some precision. But the more precision you try to give, the more you're zooming in, eventually you're going to run into the quantum. And I'm saying the quantum is like an information limit. It's the limit to where there's no
Uh,
more information, and the only thing that's left is a void. It's the symmetry. The only thing that's left is a hole, a symmetry.
okay.
And I'm
So
and
this
I'm
is
saying
where the words come from you're talking about.
yes. And so what I'm saying is that if I have a closed system like this environment, then there's a finite amount of energy and matter. So the
Okay.
information is stored in energy and matter. So if there's a finite amount of energy and matter, there's a finite resolution. And if there's a
Hmm.
finite resolution, then that means that there's like a finite amount of void associated with it. It's something like imagine the configuration of energy and matter
Mm.
is the digits 0.6523 or whatever.
Yeah.
And
So
then yeah.
so you're saying conceptually with this number line, you can have unlimited void because it's all in our mind. We don't have, but you're saying in physical reality, there has to be a finite amount of void because it has to be stored in energy and matter. And then that's,
Yeah, something like that. Yeah. Yeah.
but conceptually, we can, you know what I mean? If we're trying to do the analogy with this number line thing, then we can have an unlimited void basically. Like we
Well,
can extract it.
well,
You see what I'm saying?
yeah, no, now you're getting into the nature of like the fractal nature of
Yeah.
reality. Now,
Yeah. Yeah.
now it's something like zooming in forever, but you're always zooming in, but you never actually like get to the.
Yeah.
So
Yeah.
this question right
Mhm.
here is the foundation of like we could go on a whole discussion of spirituality from here. Like from this
Yeah.
point, you can go into the whole discussion of spirituality, the
Yeah.
idea of platonic ideals, infinite
Mm.
precision,
Yeah. Yeah.
all of that stuff. Like
Yeah.
yeah, that's where that path
But,
takes you.
but in physical reality, there's a limit because we're bound by energy and matter.
Yes, it's saying something like the way that I picture reality is that you have something like a physical side and you have a virtual side.
Mm.
Where the physical side is the configuration of energy and matter. It's the stuff that can be molded and structured.
Mm-hmm.
And then but again, because there isn't infinite precision for whatever system I have, for whatever configuration, there's a void associated with that configuration of energy and matter. And so you have to think of it as something like at every single point of reality, there is a hole. Oh, there's a hole. But if there's a hole here, there's a hole over here.
Yeah.
And so these holes have a geometry associated with them. The geometry of the
Mm.
hole is determined by the configuration of the energy and matter that makes up the hole. And
Wow.
I'm
Wow.
saying that these holes are the quantum states, and the geometry of the quantum
Mm.
states, the quantum state is defined by its geometry, which is defined by the configuration
Mm-hmm.
of energy and matter. And so these objects I'm creating are the quantum states, is what I'm saying. Like this is,
Yeah.
in other words, on reality, there's a virtual side full of these crazy geometries on the opposite side. They're all entangled and stuff.
Mm-hmm. And this configuration of energy and matter comes from, in our case, the environment.
Yeah, it's just what is the configure like why is this a pencil as opposed to like an eraser? It's
Yeah.
because the configuration of the energy and matter of the atoms and everything and how they're bonded and structured together, the configuration determines that this versus that.
Mm-hmm.
Yeah.
Okay.
Yeah.
All
And
right.
so that's what I'm trying to say what quantum states are. And so yeah, and so this is something important that I was grappling with for a while is that so what are you doing when you're creating a quantum state? What I'm saying is that you are creating voids because again, remember, the idea is something like if I have a quantum state and it's and look, I'm trying to build a quantum computer. What you don't want is decoherence. So what is decoherence? Decoherence is the process of having your quantum state interact with the environment, entangling to it, and then losing information. And so, and so what's happening when you create a quantum state is you are setting up some sort of physical apparatus, the thing that creates the quantum state. And then you're pumping energy into it.
Yes.
And this process then creates something like your quantum state. And generally you want to create a pure quantum state. Like you want to do
Yeah.
quantum computing with pure states.
Yeah.
And
So it's
so
useful.
huh?
So that it's useful.
Yeah, so that's
Mm.
useful. Well, it's like you're trying to create a pure quantum state, which everything that we've gone through, a pure quantum state means it's separable. So you're
Yeah.
erasing the correlations, you're removing correlations. If
Yes. Yes.
decoherence creates correlations, then
Mhm.
creating a quantum state removes correlations.
Yeah.
And so what you have is an object, but then you have this thing called a wave function. right?
Okay.
And the wave function is supposed to describe the quantum state, this thing that you've created, this
Yeah.
void you've created. The quantum state is supposed to describe that. And so for me, the question then became, all right, if I have this wave function that describes the state, but the state itself is separable, this wave function that has information that I can use to predict the future with.
Yeah.
And so the question I was started having is like what I'm trying to answer is what is the wave function versus what is the state? The wave
Okay.
function is your information that
Hmm.
you have about the void because of your knowledge of the physical apparatus that you use to create the void.
Okay. So the information is not lost, is what you're saying. It just transformed, is what we can say,
What
kind of.
I'm saying is something like the wave function has information about the state
Yeah.
because of your knowledge of the classical apparatus that you use to
Exactly.
create
Yeah.
the
Yeah.
state.
Yeah. Yeah. That's what I'm saying.
Yeah, and so it's something like because this quantum state, if it's pure, has no correlations to the environment. So
Mm.
so part of my issue I had is that if I have correlations, then I have the capacity to predict the future. So if the
Hmm.
quantum state has the capacity to make inferences about what I'll measure, then it
Yeah.
seems as though there's correlations here between the system and the environment, and that's
Yeah.
captured in the quantum state. But that's not the case. What's happening is that I set up my physical apparatus, I know its settings, it then creates the void by removing correlations, and then what I have left is the quantum state because of my knowledge of the apparatus, because of my
Yeah.
knowledge of the settings of the apparatus, that I now know what this void is. But the void itself, if it's actually pure, is completely separated from the environment.
Okay.
And so the important thing about this, like why is this important, is because you have to treat the wave function as an object of an observer's knowledge.
Yeah.
It's not the system. Like you have the
Uh,
system and then you have the wave function. So if you go to slide 27, that's what I'm trying to
Yeah.
represent in slide 27. So in slide 27, I have a man holding the wave function, and then I have the system sitting on a table. So
Yeah.
that's the void. And so that's something that and so within physics, this is not a settled thing. Like people argue, is the wave function the state? And it's like, no, I think the correct picture is the wave function is the knowledge that you have about the system based off of your
The physical
knowledge about
apparatus.
the classical
Yeah.
apparatus that created the system.
Yeah. Yeah. Yeah.
And so
Okay.
what that me- and so why is this important? What that
Yeah.
means is that as the system interacts with the environment and entangles with it, then your quantum state starts to lose the ability to describe the system. This is what's important. And so this is something that this physicist named Wojciech Zurek developed called quantum Darwinism. So
Okay.
in other words, what is happening is that I create the quantum state. As
Yeah.
long as that quantum state remains isolated and doesn't interact with the environment, then the wave function that I have accurately represents the state.
Present. Yeah.
But once this thing starts interacting with the environment, this wave function doesn't lose its information. It doesn't have because the geometry of the quantum state starts to change. So in other words, if I ping the quantum state, then what I have is an information flux. I have an interaction between the configuration of energy and matter that constructs the void. So I have my void and I have my configuration of energy and matter. That configuration of energy and matter, as long as it's isolated and doesn't interact, the shape of the void remains constant, and the wave
Okay.
function describes the information about the void.
Yes.
But if I were to take a part of the environment and then ping it to the configuration of energy and matter that makes up the void, then suddenly that thing carries off information. It changes the configuration of the void. And so that now takes the information and it flies off into the environment. And
Okay.
so it's something like the concentrated void I have starts to leak. It's leaking.
Yeah.
The information is leaking. And so the more it interacts, the more it leaks. And the more it leaks, the less pure it is. And then it
Yeah.
travels from a pure state to a maximally mixed state because all of that pinging entangled it to the environment.
Okay.
So that's why on your triangle, when you go from a pure state to a maximally mixed state, it's because this pinging entangled it to the environment. It's no longer isolated. It's no longer separated. The information is lost, and now you have lost in the environment, and that's why the partial trace. When you take the partial trace of the entangled state, you get random noise because it's this process of I have my pure state. It pings, entangles to a point where this pure state does not
Mhm.
represent this anymore, and now this thing has no information. That makes sense?
Yeah. Yeah. That makes sense.
Yeah. And so this picture of quantum mechanics is not like common. I don't know to what degree this is unique to me, but I'm pretty sure that this idea of defining quantum states in terms of resolution of reality, so that beyond the machine precision of reality, you have void, you have symmetry, and this is what quantum states are. I'm pretty sure that's unique to me. I call it
Yeah.
the entropic interpretation of quantum mechanics.
I haven't heard of that.
Yeah. Um, yeah, so that was the whole point to all of that. So I think that I've covered that. Yeah, and then on page 29, I have the picture of the if you look at
Bleeding
it,
out, the system bleeding
yeah,
out. Yeah.
that's the bleeding. That and I drew it that way because it's associated with a flux. That's a
Yeah.
flux happening. So you have something like your isolated volume, and then you have an information flux, an energy flux. And this is important because it's how we do things like in electromagnetism, Gauss's law, where
Yeah.
we take the electric charge and then we compute the flux,
The
the
flux.
flux going out to compute the electric field based off the charge enclosed in the volume. And then for a magnetic field, you don't have flux, you have curl. So the
Yeah.
magnetic field has curl. So in other words, it seems to me like there is a relationship between decoherence, wave function collapse, and flux. There will be a flux versus unitary transformations, which are rotations, which is going to be more like a curl.
So you're
So
trying to do the analogy between that and like information, right?
yeah, my basically what I'm saying is that my intuition is telling me that if I can work out the mathematical details of my theory and completely flesh it out, I will run into something like a flux
Mm,
associated with decoherence and a curl that's associated with something like unitary transformations.
okay.
Because they're just rotations, they're information preserving
Mm,
and transformations. I'm just taking the configuration of energy and matter and rotating it, and that doesn't create a flux.
okay.
Yeah. Were you gonna say something? Yeah. So I think that through that rant that I gave, which is always good because sometimes these things come out and sometimes they don't. But I think the environment, like the situation, created such that.
Mhm.
So now if we go to page 31, and I have written on the side, as the system interacts with the environment, its information bleeds into the environment due to entangling with it.
Yeah,
And so this is so if you look at my paper on a differential geometric approach paper, this image, huh?
I haven't. Mixed state
Oh yeah, I mean,
mixed state geometry, is that the one? Oh, no, that's
no, it's the paper I published called "A Differential Geometric
Oh, okay,
Approach to Quantum Ignorance Consistent with Entropic
okay.
Properties of Statistical Mechanics."
That's
Yeah,
different. Yeah,
yeah. So basically, this picture that I'm showing, this is me trying to describe the decoherence process, where you're going from a more pure state to a maximally mixed state at the center, where they become maximally entangled.
okay.
And so what this takes us to is the purifications and the surfaces of ignorance. So now we've gotten to the last section of this, and we're almost done.
Yeah,
But now how we have set up everything, and we understand the nature of purity and separability, and how it is the case that when you create a quantum state, assuming you've created something like a pure state in a lab, that the information you have about that state is your wave function, and that depends on your knowledge of the apparatus that created the quantum state. And once the pure state is allowed to interact with the environment, the information bleeds into the environment, and so your knowledge associated with that quantum state reduces until it interacts enough to where the quantum state you created is now completely decohered back into the environment. It's a diffusion process. It's
yeah,
diffused and relaxed back into the environment. So now your quantum state has no information in it at all, which is associated with maximum entanglement. So once the system completely interacts with the environment, it's maximally entangled, and that's why if you were to take the system now, the composite system, and do the partial trace, your wave function that you have in the subsystem has no information because it's maximally entangled. That's the whole picture.
yeah. Now it's classical, right?
What is the system?
Yeah,
Yeah, I mean now it's something like you don't have any concentrated void, and so your knowledge that you have no knowledge. Like it's almost like everything has become classical again from your perspective. But there's still, if I were to take an isolated portion and I try to zoom in to infinite precision. In other words, you can't completely separate quantum from classical. Any
mm,
system that is classical that you zoom in enough will become quantum. Like you
yeah,
can't separate classical from quantum. And this is another thing I don't know if most physicists like think of it in this detail, but yeah, every system is going to have a quantum nature to it if you just zoom in enough.
Mm-hmm.
Like I mean, it makes sense. If it is the case that as physicists we're trying to say that the foundation of reality is quantum from which everything else arises, then of course you can't just like have some classicalness that's separated from quantum. Everything has to be built on quantum.
Yeah, that's true. Yeah.
Yeah. Yeah. So okay. So all right. So let's go ahead and try to stick the landing on this. So now that we have our understanding of what's going on, like our picture, now we want to understand this concept of purifications, because the purifications is how I construct the surfaces of ignorance. They're where those geometric objects that I showed at the beginning come from, um, and they're associated with this idea of pixel. So in our last two examples, we went from the composite system to a subsystem by using a partial trace, which is equivalent to ripping a piece of paper in half. Now we want to go from the subsystem back up to the composite system. So we're going back in the other direction. And
Okay.
this process is called purification.
Well, why is it called purification?
Well, yeah, we're about to get into that. So what purifications are is for every object I have in a lower dimensional space, so I have a density operator. And say this density operator isn't pure. Say it has some mixedness to it. It has some missing information, it has some mixedness to it. For any density operator of that sort, you can assume that it came from some composite system. So think of it this way. We've already shown or discussed that for this environment system that we had, we start off with so when you're creating a quantum state, you're saying something like, I have some sort of environment, and then I've isolated a portion of it to create a quantum state. Like I separated it off, I've created this quantum state. And so this thing came from a larger composite system. Like I started off with the larger composite system of an environment that's just random, and and I haven't coalesced any void, it's just random. And then I've cooled down a portion of it, and I've sufficiently isolated it so that I've created a quantum state. So this quantum state
Okay.
came from a composite system, right?
Oh, I see. Yeah. Yeah.
It came from the
Mm.
composite system.
All right.
And so for any system like density operator that I have, you can assume that it came from some larger composite system. And so if it has missing information and we're looking at it in terms of objective ignorance, this idea of literal missing information due to entanglement with the environment, then we can always assume that there's some sort of larger composite system from which this came from. And so that is the purification. In other words, if you have a closed system, which is an environment and system, and it's closed, so there's no information and there's nothing leaking out or anything like that, then that composite system is pure. That thing is pure. So in other words, this I have my system and environment, that whole the lab and the system, and that system together is a pure state. Does that make sense?
Well, like why?
So this goes into this idea of I don't know if you heard of the Wigner-Friend problem. It's like this is like the classical
Mhm.
thought experiment in physics, where it's this idea that you can have this idea of nested quantum states. So the idea of the Wigner's friend is that you
Oh,
have a
wait.
lab.
You're assuming that we have the system and environment, and that came from a bigger environment, and then we can treat the middle one as a pure state in relation to the
Yeah,
bigger one. Is that what
yes,
you're
yes,
saying?
something like that. So
We
in
can
other
always
words,
assume there's a bigger
yes, yes,
environment
yes,
than the
yes,
one.
yes, 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 yes.
Yeah.
Always, 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 always. This goes on to ad infinitum. And actually, there's a picture that I have of
Mm.
now you're getting to the fractal nature, right? So
Okay.
now you're getting into this idea that if I have a system and it is missing information due to entanglement, then I can assume that that missing information exists in some larger system. But then if I go to that larger system and you find out that thing's mixed, then I can assume that that thing's entangled to a larger system,
Yeah.
to
Yeah.
a larger
Okay.
system, an item over and over and over again.
Yeah.
And so these are that's the process of purification. You're saying something like, okay, if I have a mixed state that is mixed due to entanglement, then I can assume that its missing information exists in the system that it's entangled to. In other words, it's like that piece of paper that I ripped in half
Yeah.
that had the message that went across the paper. It's something like, okay, I have this piece of paper and it's kind of incoherent. It says something about hot pockets, but I don't know what it's saying. I'm assuming that somewhere else there's another half of this piece of paper that if I stick these things together, I have a complete message.
But isn't part of quantum mechanics that information, once it's entangled, it's not retrievable?
No, it is retrievable. That's the whole point. It's
Always?
almost It's almost like it's something like the information just diffused into the environment, but the
Yeah.
environment's closed. It has a fixed amount of energy and matter, a fixed resolution. Like
Mhm.
it's not losing information. In other words, for the system and environment together, there is no information flux.
Uh, but
Just
that's
imagine, huh?
yeah, that's assuming the environment is limited. Like we're assuming a closed system.
Yes, exactly,
We have to
exactly.
assume a closed system. Otherwise, then no, then it's not retrievable anymore.
Yes, but then you just assume that that thing's in an even larger system.
So no information is ever lost in the universe, is what you're saying?
Well, yeah, if the
Maybe when
system,
we
if the
get
universe.
into black holes and stuff, maybe that's different.
No, no, that's correct. It's something like you have to, like, assuming the information, the universe is a closed system, then you're assuming something like a pure state of the universe, like that
Mm,
ultimately. But the thing is, and this is something that most physicists, again, there's actually Nicholas Gisson, a guy that I cite a lot in my videos. He argues against the idea that you can even conceptualize something like a pure state of the universe. So in
okay.
other words, purity, like if something's not pure, it's always because that information is lost in some other environment. And so if I can just go expand out and gain that information, then it's almost like I'm stepping outside of it. It's almost like when I'm in the laboratory, I'm inside the lab. And so because I'm inside the lab and I'm part of the lab, it's not possible for me to step outside of it. But for an observer outside the lab, they can look at me inside the lab as a contained system. And so
Okay.
this is why I would argue that the idea of a pure state, the idea that there is an articulable pure state of the universe is nonsense. And the reason why is because pure states, quantum states, the wave function is a description of knowledge of an observer. It's a description of knowledge of an observer. So if the observer himself is part of the system, then he has to separate himself from
Yeah.
reality to create a closed
Um.
system. But
Yeah.
because he's part of the system, he can
Okay.
never do that.
Yeah.
So because quantum states are associated with the information associated with an observer, and the observer can never remove himself from the
Mm,
system, so he can stand outside of it, make it closed, and see the whole thing. There's no such thing as a pure
okay.
state of the. And this again goes directly into spirituality.
Yeah.
This goes directly into spirit. We can have a whole conversation
Mhm.
going off into spirituality right now
Yeah.
because of this. It's like the God view. This is why.
Yeah.
This is why within Christianity and Buddhism, I haven't studied Islam, so I don't know. But within all of these religious thoughts, the idea that you can articulate God is nonsense. You can't. You can't have the mind of God. The mind of God itself inherently creates, like, to try to inhabit the mind of God, or as us, as what we are, we will always encounter paradox. And that
Yeah.
paradox means that this cannot be articulated. So
Mhm.
God cannot be captured in words. It's impossible. Um
Okay.
yeah, we probably didn't expect to go down that path. But the idea is that this purification process is this process that says something like, if I have a mixed state, then and that mixedness, that lack of information comes from entanglement, then there must exist some larger system that has the information that I'm missing.
Okay.
And if I have and if I know that larger system, then I can purify it by unifying it. But and I can purify it. But the problem with this is that when you go from down here to up here, pure states down here, if I have a pure state in the lower dimensional space, then the amount of information it has depends on the dimension of the space. So when we talk about information, the idea of a bit, we do it in terms of the um the logarithm of a probability. So logarithm of probability. And so the maximum amount of information you can have of a system depends on the maximum dimension, the size of the system. So for a system that only has two possible configurations, if I'm using log base 2 to compute information, then the negative log of 1/2, that equals 1. So I have 1 bit of information. So for a two-level system that can only be in state 0 or 1, the most information you can have is 1 bit. If it's a
Okay.
four-level system, you can have 2 bits. You see what I
Yeah.
mean? And so if I have a pure state in the lower dimensional space, then I have one, and it's a two-dimensional system, I have 1 bit of information. But if I then go to a composite system, which is constructed, is in our example, we had two-level systems. We multiplied them together to create a four-dimensional space.
Yeah.
So a pure state up there is going to have 2 bits of information. And so in other words, that if I have 1 bit of information, if I have say I have 0.75 bits of information, and then I purify and I go up. If I say that I know the exact pure state, then that means I went from 0.75 bits of information to 2 bits of information. I've had an increase in information.
Yeah.
That can't happen. Like, the amount of information you have is in this is the amount that you have down here, 0.75. So when I go
Okay.
from down here to up here, then I have to have the same amount of information. I can't gain any information, which means that I can't know the purification. If all I have is information down here, I can't know the purification. Then there's many pure states. So in other words, when you go from down here to up here, there are many purifications, and you don't know which one describes describes the system that completes your information down here. There are many that could. If you're missing information, then the purifications that are consistent with the information you have are not unique. They're not unique. And the number of purifications there are depends on the amount of information you have. It's this idea again. If I have less information, these are all the purifications. The information in the quantum state in the lower dimensional space, the information in the quantum state in the lower dimensional space is your constraint data. It's 0.65. And then all the purifications are everything consistent with that constraint data. But if I have more information, i.e., if it becomes more pure, then this shrinks. And if I have a pure state down here, then that means that there is no missing information. And that means that your purifications up here, the volume goes to 0.
All right.
So notice that you see the blue points that's closer to the vertex.
Yeah.
You see how when I go from the triangle up to the composite space, how it's small the closer it is to the vertex? And then as I move to the center, it gets bigger and bigger.
It's bigger. Yeah.
So because I'm moving from the one side to the center, I'm losing information, which
Okay.
means that I'm becoming more ignorant. So in other words, the constraint data is becoming less. I'm losing information. The constraint data is becoming less. It's getting bigger. And so the spread, the more purifications there are, the spread of the purifications is a direct capture of the amount of information you have down here.
Okay.
And if I have a pure state down here, then that means that pure state is separated from the environment. I have a pure state down here. It has no missing information. And because there's no missing information, then this assumption that the missing information is in some larger environment doesn't make any sense anymore, because there is no missing information. And so if it is a pure state already, then when you try to purify up to the larger space, you get there's nothing up there. It's 0 volume. You already have full information.
Yeah.
Does that make sense?
All right. Yeah. Now it makes sense.
Yeah. When you're going from lower dimension to higher dimension, the maximum amount of information you can have down here is limited by the size of the space, the dimension of the space. And so when I go from down here to up here, doing a purification process, I can't gain information, which means I can't say, oh, it definitely came from this pure state. I can't say it definitely came from one of them, because if I said I knew the pure state, then that means I somehow gained information.
Yeah.
Which, like, magically, which is not allowed. And this is the algebraic nature of this. Like, this is how it's consistent. This is how I can map points on the simplex to points up here, that to surfaces up here. That's why points on the simplex map to surfaces in the composite space, because the surface, the size of the pixel, the surface up here, how big it is, directly tells you how much information is down here. The information down here is mapped faithfully up here based off the size of the pixel.
Okay.
And so just another way to think about this is to relate it directly to the concept of information and predicting the future. It has something to do with, like, the idea, like, remember, density operators can be diagonalized. So they can be just treated as a probability distribution. So it's just a probability distribution. And depending on the distribution itself, it tells you how much information is in it. If I have a distribution of 3 possible outcomes and it's 1, 0, 0, then I have absolute certainty. I know for a fact that if I run this experiment, this is what I'll observe. But if I have a distribution of 1/3, 1/3, 1/3, I have no idea what's going to happen. I can't predict the future. So the information of the point on the simplex down here is directly related to predicting the future. It's directly to knowledge. And so that's why when I go from up here to when I purify and I go up here, that my lack of knowledge down here is directly related to the lack of which pure state is responsible for the information I have down here. And so that lack of knowledge is directly related to the spread or the size of the manifold up here. That's just another way of thinking about it. Yeah. It's all about knowledge. So in other words, at the end, this is why purifications up here, I call them the surfaces of ignorance, because these purifications itself are generated using a Lie group symmetry. Lie group symmetries are manifolds. And so there is a geometry, a manifold of purifications that map down to a single point down here. And so when I'm trying to map out the geometry of the triangle and the base space, so I have my triangle in the base space, every point on this triangle has one manifold of purifications in the composite space. And the amount of missing information is directly related. And so going back to that picture at the very beginning of the
Yeah.
conversation, where I have maximally entangled, less entangled, even less entanglement, minimum entanglement. So these are actual manifolds of purifications that I constructed using mathematics. And so what you see is that when they're maximally entangled, I have a perfect cylinder. There's
Yeah.
absolutely no separability whatsoever. When I have less entanglement, I start getting a pinching. There's a curve, and I computed the Ricci scalar curvature associated with that. So there's a pinching that happens. The more the less entangled they are. And then when they become minimally entangled, what you have in the lower right quadrant is a perfectly separable state where one is separated from the other, and I get a curvature between them reaches a singularity, a curvature singularity. And so I actually mapped out the geometry of these things, and I can study the geometry. And this geometry is directly related to entanglement based off of everything I just described to you here about how purifications are associated with missing information. And so, yeah, I don't know. Does that make sense?
No, I don't know how you moved from that to this.
Basically, go back to the picture of the triangle with the going from blue to red. Imagine that for the point on the triangle on the bottom, that those pictures I showed you, so I have a point on the triangle, like, take a look at the orange one, the middle one, and then I have this weird shape that's associated with it. So those geometries I showed you are the geometries associated with that orange circle, or like there's a blue surface, the orange one and the red one that all exist up in HES, the system and environment. Those geometries are the actual like geometries associated with that. That's for yeah, that's the actual geometries associated with that. So those are literal manifold. Those are the literal manifold of purifications. They're literal geometries of ignorance.
Still didn't understand how you correlated that with those figures at the start with the entanglement and the cylinders.
So what I'm trying to say is the whole reasoning from this entire conversation has been something like pure is associated with separability. Separability is associated with a lack of entanglement. If I have
Okay.
a pure state and it
Okay.
starts to interact with the environment, then it starts entangling to the environment. So
Okay. Yeah.
it goes from a pure state, and then it goes through a trajectory where eventually it goes to a maximally mixed state when it's
Yeah.
allowed to completely entangle with the environment.
Yeah. Yeah. Yeah.
And so because of that, when I try to take the information I have in the lower dimensional space on the triangle,
Mm-hmm.
that try to go up to the higher dimensional space, then the less information there is because of entanglement. So when this thing has less
Or less
information,
less information there is because of entanglement.
yeah, this basically you have this idea that I have my pure state. It remains pure as long as it doesn't interact with the environment. As it interacts with the environment, it entangles with it. And
Yeah.
because it entangled with it, the information I had
Is
in the pure state no longer yeah.
exact. Yeah. Okay. And then yeah, keep going. Okay.
And so as this thing entangled with the environment, the information I have decreases,
Yeah.
which causes the state, my knowledge of the state to go from pure to maximally mixed along on a trajectory along the triangle. And so since I am trying to go from my lower dimensional to the higher dimensional space using purifications, the less information I have down here, the more purifications there must be because less information down here is associated with a bigger spread. There's more pure states. Basically, think of it like this. If I had an object on the table, if I say I had 10 objects on a table and I told you to hand me an object and I wanted you to hand me one specific object, they're all different objects. And I want you to hand me one of them. Now, all I told you is that it's an object on the table. That's all the information I gave you. Then you have a 1 in 10 chance of guessing the correct one. If there were only 2 objects on the table and I did the exact same thing, you'd have a 50% chance of guessing it right. So the more objects there are, the less likely you are going to be to guess correctly what the correct object is. And so the purifications represent the symmetry of information you have. When I say hand me the object on the table, all objects on the table are symmetric with respect to that information. They're all symmetric. So in other words, if that's the only information I give you, there's no capacity for you to reduce whether or not you're
Mhm.
talking about this object or that object. You have to say, well, that's all he told me, so I have a 1 in 10 chance of guessing properly. That's exactly what's going on with the information in your density operator. I have information in density operator right down here, and the set of purifications associated with it are all consistent with the information I have down here.
Yeah.
And so because this is all the information I have to put a maximally mixed distribution on the set of purifications. I can't say one is more likely than the other. And so the more purifications there are, the more ignorant I am, the less likely I'll be able to guess which one is correct. And so as this thing moves from more information to less information, then the set of purifications up here have to grow in size in
Okay.
correspondence with the amount of information I'm losing down here.
Yeah, I get that.
And I'm saying that that's happening due to entanglement. So that
Yep.
that loss of information is happening due to entanglement. And so the geometries up here, the shape of them, the size of them, directly correspond to the amount of entanglement between this and the environment.
Okay. Yeah.
Yeah.
Understood so far.
And so these geometries are capturing something about the nature of entanglement. And so
Mhm.
when I showed you the when I sh- so I, so I'm saying something like, okay, now let's just use the math to visualize these geometries. Let's just use the math to visualize these geometries. And because I know that these geometries are directly related to entanglement, then when I look at the geometries, then in the top corner, I know that, okay, this one on the top left, this is associated with a maximally entangled state. Because, when I'm doing my mathematical calculations, I can choose what density operator I'm using. I'm gonna choose this density operator. I'm gonna make it a maximally mixed state. What does its geometry look like? Oh, it looks like a cylinder. Okay, now I'm gonna use it. Now I'm gonna choose a different point on the triangle when I'm doing my calculation. What does it look like? Oh, look, this geometry is has curvature to it. I'm gonna make it more pure. What does it look like? Oh, there's more curvature. I'm gonna make it exactly pure. What does it look like? Oh, I get a curvature singularity, which
Mhm.
I know for a fact that purity has to do with separability. And it just so happened that these geometries seem to be matching the intuition about separability. Maximal entanglement, no separability. No entanglement, minimum entanglement, maximum separability. So it's
Yeah.
just, so in other words, this is a line of research. I don't quite
Okay.
understand what's going
Why?
on there,
Okay.
but it is fascinating. And I can
It's
compute curvatures and I can analyze the geometry.
yeah. But then why is it just 2?
Um, let's see. Let me think about that. That's a good question. So these geometries themselves, they're a little bit strange. So and this might go into this might be you might have opened a bigger can of worms than you expect. So those geometries are two-dimensional slices of a larger three-dimensional geometry. So in other words, the manifold of purifications for the examples that I'm using, the number of parameters of the symmetry are 3. So the
Okay.
manifolds are actually three-dimensional.
Oh,
And so to visualize them, I have to take two-dimensional slices. So what those are actually two-dimensional slices of the full three-dimensional manifold of surface of ignorance, manifold of purifications.
that was what's missing because that's what I was
So
confused
yeah,
about.
so I don't actually know. What I do know is that when computing fidelity, I do know that when I compute fidelity, that I can go to a two-dimensional subspace, a slice of the three-dimensional manifold, and it's still sufficient to compute fidelity.
Mhm.
So I know that within this two-dimensional submanifold that I have access to the space, a sufficient access to the space to be able to compute fidelity in that space.
Mhm.
And so in that regard, there's something about a lack of missing information from going from a three-dimensional full manifold to a two-dimensional slice, but this is part of research. I don't actually know. I don't
Mhm.
know.
Mhm.
This is a big open question. All I know is that it's very curious that I get this nature, and then also I can show you how I can do rotations of the triangle. I can rotate the triangles, and that corresponds to changes in
Yeah.
phase.
We've talked about that before.
Yeah. So now we're starting to get deep into like the actual research because one thing, if you're like a theoretical physicist, especially a quantum physicist, and you're looking at this, you'll notice that the mathematics is simple. Like, in other words, I think that my research program, if I was a professor and I had students, I could unleash my students on this space like mad because it's so simple mathematically. It would take me probably like a week or two to explain to them the mathematics, but the actual implications and what's going on is so deep and there's so much to study. Basically, there's a shit ton of low hanging fruit.
Yeah,
There's a lot of it. And I can literally train people on the internet if from watching these videos what the calculations are, what the math is, and then unleash them to do actual physics
yeah.
because there's so much to do here.
Well, why don't you start a Discord?
I don't know. Time. I don't know. I mean, if I were to get traction, if I got more people inquiring, sending me messages, curious and interested, then I would.
Yeah.
All I need is something to tell me that it's worth my time.
Hmm.
But yeah, and that being said, like, if you're watching this video and you actually made it to the end, which would be shocking, but if you did, then you're clearly interested. Don't forget to subscribe to the channel, like the video, and share it with anyone else that you think might be interested. Because yeah, this I don't know. If it was up to me, this is all I would do is this research. I need the funding. I need money. But anyway, are there any other questions or any other ideas?
I'll definitely come back to you with some questions.
Okay. All right,
Uh,
sounds good, man. Hopefully this made some sense.